We're going to start by looking at the Module 2 organic material. Now, there are 3 mechanisms that you have to learn in this syllabus, and we're going to go through them nice and slowly, but we're going to cover them all this morning. The first one is called free radical substitution. Now, the thing about mechanisms is that pupils find them a little bit tricky. But once you get your head around them, they're relatively straightforward, and I guarantee these are going to be in the exam. Because there's so few mechanisms, they usually ask all of them. Okay? So I wanted to start this session by saying the word mechanism equals, label it in your mind as, I've got to understand this, and I've got to learn this. So, alkanes, as you should know, are quite unreactive. Their chemistry is based on, the chemistry so far you've done to differentiate between alkanes and alkenes is based on the fact that alkenes react and alkanes don't. Remember that? Remember the test for the alkenes? Is you add bromine water, and the bromine water decolorizes. Remember this? Yeah. Yes, good. The whole point is the alkenes react and the alkanes don't. Yes? So, they're quite unreactive. But there is a way of making them react, and that's what we're going to be looking at this morning. To begin with, I want to give you some terms, and this is actually going to help you with the Module 1 stuff because it talks about intermediates. There are 3 ways of splitting a covalent bond. Remember, a covalent bond is a pair of shared electrons. You can split a bond so that both electrons end up on one side, like so. Okay? So you get a minus and a plus. You happy with that? Or you can split it the other way, so you get a plus and a minus. Or you can split it like this. Okay? Now this is called homolytic fission. Very simply, fission means splitting, and homolytic means of the same kind. So homolytic fission means splitting it in the same way. And what happens is one electron goes one way, and the other electron goes the other way. Notice, please, there's no charge on either of these species. Neither of them are positive, neither of them are negative. You happy with that? But both of them have this red dot represented here. Now, by convention, a dot in the middle, not at the top, not at the bottom, but in the middle, means a free radical. Okay? And that's what these are. These are both free radicals. They're not ions, they're free radicals, and they have, critically, a single unpaired electron. Say that again. They've got a single unpaired electron. So they're represented with the dot. You happy with that? So very quickly, again from the top, here, both electrons, covalent bond, pair of shared electrons, both electrons have ended up on the X. The X is negative because it's got an extra electron. The Y is positive because it's got one less. Here, it's the other way around. And here, the electrons have gone their separate ways. It is split up in the same manner, and that is homolytic fission. Everyone with me so far? We say at this point, I don't mind you stopping me and asking questions. The only thing I will say about that is if you do say your voice in a loud manner, it will end up on the podcast. So, you know, no swearing, and please don't mind about that. Happy with that? Okay. Double overshoot. So, free radicals possess an unpaired electron. Already said that. Very, very important. And they're very reactive. It is thought that most of the aging process, or a significant amount of the aging process, is down to free radicals in your body. Okay? I remember hearing a long time ago that somebody had genetically bred a fruit fly that was able to mop up oxygen-free radicals at a much greater rate. And these fruit flies lived twice as long as other fruit flies. Okay? And were healthier during that lifetime as well. So radicals are extremely reactive. We've said they're formed by homolytic fission of covalent bonds, and, as we're going to come to in a minute, they're formed during the reaction between chlorine and methane. But importantly, and this is a bit from Module 1, they're formed through thermal cracking. Do you remember with cracking you have thermal cracking and catalytic cracking? Yeah? With thermal cracking, it undergoes homolytic fission, and you end up with two free radicals. Happy with that? You just heat it up, covalent bond breaks, both sides take an electron, and so on. We got a question? No? All right. And importantly, we're going to come to some ozone layer chemistry in a little bit, which you're expected to know from memory. Just want to flag that now. Okay. This is probably the big reaction. This is the one that's mentioned in the syllabus. The reaction of chlorine and methane. The bottom line is, if I get some chlorine and I mix it with methane and I sit there, you know, maybe sing a little song to it, something like that, absolutely nothing happens if I do it in the dark. But if I do it in sunlight, they start reacting together. And the first major important point I want to make about this reaction is it requires UV light or sunlight. Regular light from these sorts of things doesn't cut it. Okay, you need UV light. And once the reaction is done, you get all sorts of stuff. And we'll talk about specific reactions in a minute. But at this point, I want to say, if you start with methane, chlorine, you can get chloromethane, dichloromethane, trichloromethane, and even tetrachloromethane, which used to be called carbon tetrachloride, but is no more. Happy with that? And we'll talk about how in a minute. Right. This mechanism is called free radical substitution. Okay? There are going to be some long words this morning. I'm going to use the words nucleophilic later. But to start with, we're going to talk about free radical substitution. I'm not going to explain that bit yet, because I want to talk about this bit. Okay. Chlorine. With a bit of UV light. Okay? Just write UV light in your notes next to it. You've got space to do this. UV light with chlorine creates two chlorine radicals. Okay? Here are my chlorine radicals. You happy with that? Okay? And I want you to label this as initiation. All right? This is called an initiation step. It's a step where a molecule becomes radicals. Happy with that? We started with a molecule, we've hit it with some UV light, the UV light has given enough energy to the bond to break up, and we've created two chlorine radicals. All good so far? Good. In slightly more detail, a C to H bond has got a bond enthalpy of about 412 kilojoules per mole. A C to C bond, 348 kilojoules per mole, but a Cl to Cl bond, 242. A Cl to Cl bond is significantly weaker than any of the bonds in an alkane. Okay? But now these chaps, well, these guys are a bit reactive. And what you'll see now is how they react with the rest of the molecule. Okay. Very simply, a radical can react with a molecule. That's hardly surprising. I've been saying for the last few minutes how reactive radicals are. Yes? We formed a radical by hitting some chlorine with some UV light. We've got a radical. We're now going to hit it. We're now going to react it with methane. Chlorine plus methane forms a radical and a molecule. Chlorine plus the methane forms a radical and a molecule. The radical effectively rips a hydrogen off the methane. Are we all good? But I said that we form things like chloromethane, which is that. And we haven't. We've just formed that. This is not the end of the process. This step here is called propagation. We've had initiation, and now we've got propagation. Are we happy with the use of the word propagation? We know what it means in English. No? It means to carry on. Okay? Propagation means to carry on and to make something new. Okay? If common term for it is plant propagation, where you take a small cutting from a plant, stick it in some soil, water it, give it some hormone, blah, 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 you get a new plant. Yes? You haven't killed the original one, but you've got a new one. So propagation means to continue to make new ones. This is a propagation step. And very importantly, radical plus molecule goes to radical plus molecule. Okay? We have not destroyed our radical. We've changed it. Okay? We've turned one thing that was a radical into a molecule, we've turned a molecule into a radical. With me so far? Great. Process doesn't end there. Chlorine can now react with this radical, okay, without the need of any further UV light. The chlorine reacts with the radical, forms a molecule, and you're back with a chlorine radical to begin with, as you begun with, rather. Does that make sense? This, again, is propagation. We'll talk about termination in a minute. So, to recap, when my mouse wakes up, this is an initiation step. Okay? You need the UV light to break the molecule apart and form the radicals. Once you've got the radicals can react with other molecules to form different radicals and other molecules. You got it? This little chap here can react with that. It could react with something else. Okay? It could react with a Cl dot. And what you could get is this happening here, where Cl dot reacts with CH3 dot and forms CH3Cl. And that's called a termination step. The termination step is where two radicals react together and form a molecule. So critically, we have three steps. We have initiation, okay? Molecule being broken into radicals. We have propagation, where a molecule and a radical react to form a molecule and a radical. You with me? And we then have termination, where two radicals react together, form a molecule. All good? It's the desks, isn't it? They've produced mute silence in absolutely everyone. Are we happy with this? Yeah. Yep. Good, good. So, here are some diagrams representing that. Radicals forming a molecule, radicals forming a molecule, radicals forming a molecule. Starting with methane, you can make just about any haloalkane. In this case, this ethane could now react with a chlorine radical, and you could get chloroethane. Yeah? Can you see that? The mark scheme, the syllabus specifically talks about the reaction of chlorine and methane. But I think you should realise, if you start with chlorine and methane, you can make chloromethane, dichloromethane, trichloromethane, tetrachloromethane, ethane, chloroethane, dichloroethane, and so on. Yeah? Just by different bits coming off and so on. And that's that. Initiation, propagation, termination. Examples of different steps, but you need to know those three words. You need to know what those three words consist of in terms of the meaning and the reactions involved. Okay. And some pretty diagrams and some further propagation steps to produce things like dichloromethane, trichloromethane, tetrachloromethane, and that's the end of that one. Okay. Any questions at this point about anything I've covered so far? No? Are we good? You can pause for a second. We're going to pick up on a few general green issues to do with the chemistry of the air. We're going to cover global warming for the umpteenth time. We're also going to be looking at ozone chemistry. Now, the ozone chemistry came up in last summer's exam and was atrociously answered by my pupils. Okay? The thing was, I had taught it, but it doesn't come up in the Hench booklets because it's new to the syllabus and the pupils had completely forgotten it and so on. So I want to flag the ozone chemistry. You've got to know it, okay? Because it's quite likely to come up, and if it does come up, I'd want you to do a lot better than last year's Year 12 did. Right. Greenhouse gases, first of all. Oh, got a little bit of battery this time. For a molecule to be a greenhouse gas, it has to have at least 3 atoms. Okay? Carbon monoxide is not a greenhouse gas because it's only got 2 atoms. Nitrogen is not a greenhouse gas because it's only got 2 atoms. But anything with 3 or above can start absorbing infrared light, okay, in the particular frequencies. So these 3 are all greenhouse gases. There is significantly more water than there is of the other 2 in the atmosphere, but this one here is a significantly more potent greenhouse gas. And one of the big debates at the moment is about the amount of methane that is released, because it's so much more powerful as a greenhouse gas than carbon dioxide. So, the thing about these molecules is they all absorb infrared light. Okay? And what we're going to be looking at a bit later on is spectroscopy and the link between infrared spectroscopy and the greenhouse effect. But all these molecules absorb infrared light. And they absorb it by the bond vibrating or stretching in a certain way. So if you imagine a water molecule for a minute, you've got the oxygen in the centre, you've got the hydrogens to either side. That hydrogen can bounce in and out, it can flop up and down, it can rotate round. Okay? Any one of those things, okay, can absorb infrared light. So there's a certain bit of infrared light that makes it do that. There's a different bit of infrared light that makes it go around like that, and so on. Okay? These, bending, stretching, and so on, absorb infrared light. And we're going to be looking at that in more detail in spectroscopy. But they occur at a different frequency, and that's the point I'm trying to make now. And we have a nice little graphic there. Okay? Symmetric stretching, bending, asymmetric stretching, and you all do also get this rotating of groups as well. And that's nice and pretty, that is. Carbon dioxide can do that. Okay, there it is doing the press-ups on the screen, moving up and down. And, well, let's talk about this now. This is an infrared spectrum, and it looks hideously complicated, and in truth they are hideously complicated. At A level, all you are really required to do is take a peek, read off a number, and look it up against data that you're given in an exam. Okay? You remember you get a data sheet, there's one at the front of your Hench booklet. On that data sheet, it has a table of functional groups versus wave numbers, which are the units that we use for infrared spectroscopy. All you have to do is go, aha, this peak here is about 1650. You look it up, what's got a peak at 1650? C double bond O, therefore that peak is due to a C double bond O. It's as simple as that at A level. And we will talk more about infrared spectroscopy. But the point I'm trying to make is that all of these absorptions, all of those absorptions, okay, are in the infrared region. All of these molecules absorb infrared light. So the greenhouse effect. Now this should all be very, very familiar to you. Energy in the visible light region and the ultraviolet region and so on comes down from space, and a lot of it hits the Earth. Radiation is re-emitted from the Earth in the infrared region. Basically, it warms the Earth up. When it warms the Earth up, the Earth gets warm and gives off infrared light, which goes up into the atmosphere. And a lot of it goes to space, but the greenhouse gases absorb the rest. And the energy is returned to the Earth to keep it warm. A really simple example of this is that you know a cloudy night is a warmer night than a cloudless night. Yeah? If you go out of your house at 9 o'clock on a winter's evening and you look up and you see the stars, the chances are there's going to be frost on the ground, probably quite a bit of it. If you go out at 9 o'clock and you've got a lot of cloud over, it's going to be a much warmer night. There might still be some frost, but cloudy nights are much warmer than cloudless nights. And that's because the cloud effectively acts as a blanket over the surface of the Earth and keeps the heat in. Whereas a cloudless night, a lot of the heat is just radiated out into space. So it's colder. Happy with that? And so on and so forth. We're not going to worry about these numbers to begin with, but that's the greenhouse effect. But what I'm wanting you to link to is, what I'm wanting you to understand from an A-level point of view, is that it's due to the absorption of infrared light by the stretching, vibrating and bending of bonds. Happy with that? Good stuff. So, possible effects of global warming, you're all doomed, blah, 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 and so on. Carbon capture and storage, or carbon sequestration, is unlikely to come up in the exam, but you should know that carbon dioxide can be put it into underground storage where things have been mined. You can now store carbon dioxide and so on. It's one of those, we could do this if we tried really hard sort of things, but nobody is doing it at the moment. There have been a few tests done, but there are no power stations which capture the carbon dioxide form. And I'm going to skip through all of that very, very quickly. Right, ozone layer. Most importantly, lads, the ozone layer is not the same problem as the greenhouse effect. Okay, and I still see A-level pupils make that mistake, thinking these two are the same thing. They're not. Okay? Very simply, ozone is a reactive poisonous gas. It protects the Earth from UV radiation. Okay? And without an ozone layer, there will be much higher rates of skin cancer amongst people. Okay? This is the really, really important bits. Ozone is O3. Okay? Not O2, O3. There are two different molecules that are both elemental oxygen. O2 and O3. O2 is the stuff that you're breathing now. O3 is very, very different. Okay? O3 and O2 can turn into each other. Okay? They can react. One can form the other. And importantly, this occurs through a free radical mechanism. Okay? Ultraviolet light can supply the energy for this process. Okay? Ultraviolet light can break up the ozone. And what is actually occurring is a natural equilibrium between O2 and O3 catalyzed by UV light from space. Okay? The UV light comes along, can hit an O2, can break it up, and the O2s can then react, so that the O radicals can then react with an O2 molecule to form an O3. Yeah? And the O3s can get zapped by a radical, they can break down, form O2 and a radical, and so on. And you end up with a nice equilibrium, UV layer, lower rates of skin cancer, we're all happy, yes? Needless to say, there's been a bit of a problem. And the problem has been these little chappies here, CFCs, chlorofluorocarbons. Now these have been around since the 1920s, 1930s. They were developed as refrigerants and as fire-retarding systems. Okay? They're gases, they can be used in fridges, they're non-flammable, and so on. There's only one problem. When released into the atmosphere, they can get zapped. And in this case, put a dot, please, after that. CCl2, F2 goes to Cl dot plus CClF2 dot. What type of step's that? Initiation. A molecule goes to two radicals. Yes? We get an initiation step. Now, here's the bit that was asked for last summer. Here's the bit that we got a total of like 17% of the marks available. O3 reacts with a chlorine radical to form ClO dot plus O2. ClO dot plus O. I don't like that. No, we're going to do a slight aside here if you can track me.
Oh, sugar.
Okay. O3 plus Cl dot goes to ClO dot plus O2. We happy with that? Yep. ClO dot plus O3 goes to 2O2 plus Cl dot. It turns out that there are a number of different oversimplifications that are floating about. But correct me if I'm wrong, but I think that this is what's in your textbook and this is what's in the syllabus. And this is what I'd like you to learn at this point. Okay? Ozone reacts with a chlorine radical. Just make those dots slightly bigger so they can be seen on the film. Forms a chlorine-oxygen radical plus O2. You happy with that? That then reacts with another O3 to form 2O2 and Cl dot. What do we notice about this reaction?
It destroys ozone.
It destroys the ozone. And what else do we notice about it? Yep. There's no O3 being produced. Yep. What else do we notice?
Not terminated?
It's not terminating, no. We started with a chlorine radical, we finished with a chlorine radical. I remember hearing a long time ago that they reckoned a single chlorine radical would destroy 50,000 ozone molecules before being taken out of the loop. Okay? These things destroy huge tracts of ozone, to the extent that there is now a hole in the ozone layer above Antarctica. The good news though, okay, when it comes to environmental issues, this is now a good news story. People identified the ozone was getting thinner. They identified why the ozone was getting thinner. They took steps, they banned the chemicals that were involved in thinning the ozone, and the ozone is now getting thicker. Okay, the hole is beginning to close up, the ozone layer is getting thicker, and back in the 80s it was absolute certain by 2020 you couldn't go outside because there wasn't going to be an ozone layer, 7 seconds in the sun, you'd all get skin cancer. Okay? Actually, we're okay. But this is a really good example where chemistry, okay, created a problem was identified, and has been solved because they've been able to use something else. Okay? And the real problem with the greenhouse effect is that people are struggling to find other ways of doing the same thing, namely produce large-scale amounts of electricity. Whereas the CFC problem was due to some specific chemicals, okay, and has now been rectified, or pretty much rectified. After that, there are all sorts of other reactions that can take place. O3 can be broken up by NO, and so on. I want to talk briefly about pollutants from internal combustion engines, and then I think we're about done on this session. Firstly, carbon monoxide comes from incomplete combustion of hydrocarbons in petrol. Are we happy with that? If you've not got enough oxygen, you make carbon monoxide rather than carbon dioxide. It's poisonous, it combines with hemoglobin in blood, and it prevents oxygen being carried to the cells. Okay, so your heart's pumping, your blood's going round, your lungs are working, but the blood can't carry oxygen. Not very pleasant. Other ones. You'll sometimes see this written, NOx, okay? And that just means that it could be any combination of nitrogen and oxygen. So we get NO, N2O, and NO2. Okay? This one, the medics amongst you should know as Entonox, and the petrol heads amongst you should know as NOS. It's exactly the same stuff. Okay? It's laughing gas. It's an anesthetic, okay? But it's also used to enrich the air intake on cars. You've used it, was that?
Yeah, 3 weeks ago.
All right. And it was that one, wasn't it? Yeah. Basically, that breaks down and forms 2 parts nitrogen, 1 part oxygen, which means the mixture is a 1/3 oxygen. Air is only a 1/5 oxygen. So by using that instead of an air intake, okay, you increase the availability of oxygen, you get a purer burning, Okay, and unless your engine is particularly well designed, okay, the pistons go down through the bottom of the engine, conrod breaks, and the engine blows up. Don't do it to your parents' cars, all right? Moving swiftly on. These guys, they all combine, they react with all sorts of other stuff, and you end up with photochemical smog. Classic sort of picture of Los Angeles taken up from the Hollywood Hills. Okay, great big sort of smoggy layer over the city. That's this, it's that once it's combined with unburnt petrol, and you get photochemical smog where everything's reacted with everything else. You get all sorts of different hydrocarbons, nitrogen oxides, and so on, and it's a mess. You get the unburnt hydrocarbons, they're toxic and carcinogenic, which means they cause cancer, which is why, where I think we're going with all of this, is catalytic converters. Catalytic converters convert carbon monoxide to dioxide, they convert the NOx's to N2, and they convert the unburnt hydrocarbons to CO2. Okay? So catalytic converters are really good because they take care of all this pollution, okay, and just chuck out N2, which is in the air anyway, and CO2, which is a greenhouse gas, but is less bad for people than unburnt hydrocarbons and carbon monoxide. You happy with that? And so on. Catalysts are rare metals such as rhodium and palladium. Okay? You can also put platinum in there. My wedding ring is platinum, and when I bought it, it was about £100 worth of platinum, and I think now it's about £300 worth of platinum. There's not very much to it. Okay? You have to have your platinum or your other precious metal over a very fine surface to create a really large surface area. Okay, a big old block of platinum, okay, would not do very much, and it would cost tens of thousands, hundreds of thousands of pounds. So what you want to do is take a small amount of the metal and spread it very thinly over a surface. And we're not going to look at this now. We're not going to do that. We're going to call it a close there. Okay, pause please.